is
you
being
just,
recorded.
yeah, Dave, there are a bunch of them. I just admitted them.
Okay, let me get my screen straightened up here and then I'll share. Okay, let me, it might be an issue here, control. Okay, Dave, I'm gonna grab the screen. Go ahead. Okay, so I'm sharing the pre-assessment score. So we have 16 questions, and the average is 125, which means about a little over 12 questions was answered correctly. And then the range is from 70 to 160. So I think 125 over 60 is pretty good. So you guys did watch the videos and understood most of it. It was great. Okay, so let's move to the lesson. So this is lecture 11. This is placements part 3. So we've gone to 2 placement lecture. We've covered from sanity checks all the way to timing up. And today we're going to talk about power and area ops, tie cell insertion, and also how to add spare cells. And then I have a couple of slides on introduction to MBFF. This is for multi-bit flip-flops. If we have time, we may also go to the next topic, congestion analysis. That depends because the lecture 12 we got lab instruction. Okay, so we're talking about power analysis. This is power dissipation and not rail analysis. Okay, so this is basically the power components that the design use, how much power it use. So before we understand what power analysis is, let's jump in, understand the power components. So in the design, we have what's called static and dynamic power dissipation in design. So static meaning that even when the cell is not switching or not not switching, just in static mode, there's still a leakage powers through it. Okay, we'll discuss that in detail. And then the second part is dynamic power, which is the power, the switching power when the cell actually turn on and off, or charging or discharging the load, capacitive loading. Okay, and then power simulation usually done throughout the design cycle. They do it as early as RTL, but of course that's not accurate as you do it once all your cells are in and all your placements and routings are in, your clock trees are in. That's more accurate as you move down toward the post-route stage. Okay, so this is just showing the total power dissipation in the design. So you have static component and you have dynamic. So static just the leakage through the transistor, and then the dynamic is the portion where the output actually switching, which incur power. Okay, so within the dynamic and static power, there actually is 3 different components. Dynamic broken into 2. So in dynamic, you have switching current, and then also what's called internal power, which is the moment. There's a short moment where the P and the N short together, so there's a leakage, right? There's a current right through the P node to the N node. So that's considered part of dynamic, and then of course the static is the leakage current. So what is the static power? Okay, I mentioned before, dynamic. Dynamic when logic gate change from state 0 to 1 and 1 to 0. So basically here's the output, right? The capacitor loading switching from 1 to 0, 1 or 0 to 1. And it is frequency dependent. So the faster the frequency, the faster your gate operate or design operate, it's going to switch faster. Therefore, the faster switching, right, it's gonna incur more power, right? And also depend on the output loading also. And then the VDD supply. So the higher VDD, the more power it's going to use. So for example, your cell phone, right? Your cell phone is about 0.9 volt. It's much lower than versus your, let's say your something to plug in your laptop. That's usually at high volts are like 3 volt. So it's going to use a lot more power. Okay. And then the AF, which is called the switching activity factor. So in your design, not at a single moment, not every node, every node going to switch. So in order to calculate more accurate, you need a switching activity from some sort of gate simulations. So usually they take throughout the simulation vector, they take a vector or portion of the vectors where there's most activity. So that's what they normally use to feed in the to figure the power. It's more accurate that way. Okay, so the next power is called internal power. So this is also considered dynamic. So this is basically doing the output switching from 1 0 0 1. So there's a momentary that the P and the N will short together. So that causes a little bit of a short current flow through the transistor. So this is also dependent on the frequency. This is dynamic, okay, and then the short circuit current through the NMOS. So this short circuits also depend on the time of short circuits, right? So if it's longer, then it incur more power, right? More leakage through here. So for example, if you have a transition, right? The output transition is slow. That means that it takes longer to switch from a zero high or high to low. So that means the short current, this TSC, right, his short circuit time is going to be longer. Therefore, there's going to be more internal current through the transistor. Okay, so basically the internal power also proportion to your transition time, right? It's faster, it's going to be less internal power. Right? If it's slower, then you incur more the TSC, the short circuit time will be longer, therefore there's more currents going to leak through. So it's like a gate, right? If you shut the gate off, you have water flow through it. If you shut off faster, the less water flow through. Versus, if you leave it longer, then the more water go through the hose. Okay, so usually internal power is usually less than 10% of your dynamic power. Okay, so it's shouldn't see that much more. Okay, so the last part of component power is static power. So this is regardless what you do, regardless of the speed and so on, it doesn't really matter. So this is leakage when the transistor is sitting there, not doing anything. So it's a function of VDD. So it's VDD time the leakage current. Okay, so let's talk about a little bit about the leakage current. So the leakage current really is three components. There is what's called gate leakage current, which is leaking through the gate. So this is also known as a gate oxide tunneling. So the current flow result of the electric field at the gate and also at the drain. So that causes a tunnel where the electrons flow through. So that's what's called a gate leaking current. The second part is called subthreshold leaking current. So this is this guy here. So it's happening when the gate voltage thresh is below the threshold voltage, then it causes the current to flow from the drain to source. Right. And the last one is called reverse bias leakage current. So occur when the drain is source NMOS VD or the PMOS at ground. Then we have a reverse PN diode form, and then source drain causes current to flow through the substrate. So that's the three components of the leakage current. So this is so remember in last lecture when I mentioned the high VT and low VT, the lower the VT threshold, the higher the leakage is going to be, right? So that's the function. So this is a quick summary of the total power dissipation in the circuit. So we have the switching, P short, a short circuit, and a power leakage. So here, this is all the equations that just a quick summary. Okay, any questions or additional inputs from the instructor before I move on to the next one? See, there's Dave, we have any questions in the chat?
No questions so far. And students, we do encourage you to ask questions. So please, if anything's not clear or if you'd like to expand on something, let us know.
Phil, you guys have anything you want to add or elaborate on?
No, except for some observations. Sometimes maybe it's easier to read if you zoom in. Like for example, in this slide, it's very difficult to read on the right, right? So
Oh, you mean the this
yeah,
portion?
whenever you can just zoom in, it's easier to follow.
Okay.
And perhaps speaking a little bit slower. Yeah.
Okay. I will try. Yeah, I tend to speak a little faster. Okay, thanks for the input. Okay, so this is the leakage versus dynamic power trend. So this graph here is showing you this is the power. Basically, it's going up vertically. And this x-axis, this is the device technology in nanometers. So this is 250 nanometer to 50. So the geometry or technology node is shrinking as you're moving toward the right. Okay, so you can see the purple represent the leakage current, and then this gold color represent the dynamic current. So as you at the geometry gets smaller, you can see the leakage become a bigger factor. Okay, you can see that it's increased bigger factor. So in today we're at 3 nanometers. So imagine this, the leakage is going to be dominate. So it's a huge challenge for designers and PDs to reduce the leakage, right? So the reason leakage increase exponentially in lower geometry is because at a lower voltage, right, you're going to have a lower VT, lower threshold, voltage threshold. Therefore, the leakage is going to increase. Okay. Also, at lower geometry, your gate oxide can be a lot thinner. Therefore, it's much easier for electron to tunnel through. So therefore, your leakage also increase. Okay, that makes sense. I don't have the slides showing you all the way down to 3 nanometers. But I mean, this one will kind of show you the trend. Okay, this is just a slides on, this is actually the part of the lab, Innovus lab, where we actually do the report power, do a power analysis. So I just want to show you the result here. You can see there's 3 components of the power that we just spoke about. This is done in placement, so we don't have any gate activity inputs from simulation. So we just set a default activity, switch activity, which here is 20%. So this number may, it depends on your designs and then and so on. So you get this input activity factors from your designers or from the team. So here I just said it's 20, and then of course the clock period is 8. And notice the switching power is only 5, okay, milliwatts. Anybody think of why it's only 5? Usually the switching activity is going to dynamics going to be a lot more than the leakage, right? I mean, than the internal power, right? This is only supposed to be 10%. Can anybody think of the reason? I mean, you can just put in the chat. I'll give you a few minutes to think, and this why the switching is only 5 versus internal. Anyone take a stab at it? Yeah, just a little bit. Okay, so no one. All right, the reason is, remember, clock tree is a big portion of the switching, right? So in placement, we don't have the clock tree yet. So the clock tree is there's no clock tree. That's the reason why the leakage is currently low. So when we build the clock tree, expect these numbers to grow up to be a lot bigger. Okay, so here the leakage dominate. Okay. So here it breaks, just give you a breakdown difference between sequential, macro, IO. Our design don't have any IO, so you can see there's none. So sequential basis flip-flops and combinatorial logics is and or gate and so on. So it did give you a breakdown pretty detailed. So this is just a summary. So you'll see this in the lab. Okay. Okay, so next topic is power optimizations. So what happened during power optimization? Okay. So we're swapping cells. First is swapping cell for lower power. So basically, you have usually happen is when you do power up, usually it does it on a non-critical nets. So meaning that nets that has extra margin is going to try to downsize. So you have like a AX going to try to downsize to a 4X, or a low VT is going to swap for a I mean, a high VT is going to swap for a low VT is going to swap for a high VT. So where you don't need the speed, but you need to reduce power. Also, it will delete some of the buffer inverters if it can still meet DRVs. Yeah. So this is just another set of commands here. We have to set input switching activities. Okay, here we set a global and activity is 20%. So meaning that 20% of the everything's gonna switch at 20% of the time out of one cycle is gonna switch 20% of the time. And sequential activities is flip-flop. Flip-flop usually switch more because it's connect to the clock tree. So we'll assume it's 80% of the time. So this maybe too pessimistic. It depends your design, right? So this is an early guesstimate or estimate. Okay, here I have a command here says set DB obligates to dynamic, basically telling it to optimize 50% dynamic and 50% leakage. Actually, at this stage, since there's no clock, we could just do all leakage, okay, and set it to 1. Okay. Oh, this is just a repeat. Okay, so to run power up in Innovus, you just do up_power. That's pre-CTS after you set your activities, and you should be able to generate the report. Actually, you'll be able to see the tool does the power up. So this is the log of the power ups. As you can see, what's happening here. As it commits, meaning that it make changes, right? So you can see this memory real in slack. So the slack still met, and density is 55. Okay. So at the end, you have to do report power to see what the power number would be. So this is just a log from Innovus. Okay, so that was power. Any questions on power dissipation? Remember, we had 3 different type of power. You have switching power, internal power, which is a short circuit power, and then you have the leakage power. So at the low geometry, the leakage power is one of the most challenging to manage for designers. At a higher node, not so much, because the leakage power is only a portion of the total power.
Students, if you're reluctant to ask a direct question or to slow down, don't forget that you can use the reactions button to let us know that you're either understanding or you'd like us to speed up or slow down on the instruction.
Okay, so this is just the summary page. Okay, no questions. We can move on to the next slide.
But can I add something for
Sure.
power? Yeah. Can you go back to page 85? Yeah. So first of all, in general, you go and do the timing analysis. You try to meet timing. Timing closure is the most challenging, and you do power as a side optimizations, because if your timing is not met, then the chip is not operational. Power is being saved and optimized because it impact your performance, right? Your chip performance. So can anyone tell me, if you design an SoC for an iPhone or a smartphone, which power component of power is the most important to be optimized for? Is that internal power in here, switching power, leakage power, or total power? Can you what is the most important one? Can you type in the chat which component is the most important to optimize for handheld applications?
And by the way, most of the like the Samsung Galaxy or the iPhone 15, those currently at the TSMC 3nm geometry. So that's currently the most advanced on the market.
Lê Minh Hoàng, leakage power. Thank you. Lê Thanh Trung, switching power. Please continue to answer. Dynamic power, Đức Anh. So leakage power, Phạm Minh Trí. So the most important power component is leakage power. The reason is this: most of the time, when using leakage, thank you. So most of the time, your phone is sitting there doing nothing. So when your phone is not receiving call or playing a video, when you play a video, that's when the circuitries or receiving a phone call, that's when the internal circuitries doing stuff, signal processing, basically. When you have a voice coming in, your phone has to sample the voice or the music, do an A to D, analog to digital, and do filtering, do all kinds of processing to give you the best sound or best pictures. So when the phone does that, it will consume the dynamic power, right? And switching power. But most of the time, the phone just sits there And when nothing's switching, then leakage is the one who's killing your battery life. So your phone will be sitting there and just leak. So constantly leak days after day. So the most important one is leakage power. So if you are not working on a handheld device handheld applications or wireless applications, and your device is plugged in, for example, you have a chip that plugged in a base station or plug in a 5G system box somewhere, then dynamic power is going to be a problem, because if usually when your chip is in those kind of plug directly use get the BDDs, get the power from the board. Typically you running at a very high speed in a very hot environment. So dynamic power management becomes important as you want to manage heat and also. So back in here in page 15, you see the but the power analysis, the power consumption is really, really difficult to simulate, simply because for leakage, it's easy. Leakage is just a total source drain area or gate area. As you recall, the gate leakage is the most important, the most dominating source of leakage. But the source and drain and gate leakages can be calculated by calculating the total of active areas. But for switching, it's really depending on the switching activities on internal nodes. And switching activities is dependent on what you're simulating. For example, if you do a DSP on signal processing of your signals, or you're doing a graphic processing, the internal circuitries, how often they switch, will result in how much power it draws. So in here you see set default switching activity and / input activity. That means all the input, you assume a 20% of switching, meaning that for each clock period of 8 nanosecond here, your input switch 20%, but that's the primary inputs, meaning the IOs. What happens to the internal nodes? If you don't switch, you don't set the activities on the internal nodes, and what the tool does is that it will calculate based on some algorithm, probability algorithm, based on the nature of your logic internally, to calculate the switching activities on each and every node. If you have 10 billion transistors, it's going to be 4 billion node, for example. So each of them have to have a switching activity, and the lookup table will tell you how much power each gate, each transistor draw for the analysis that you are doing. But the most accurate one will be running simulation, for example, running a speech processing, loop, and setting up everything, and after that you will be able to extract the switching activities on all the nodes and more accurately based on simulations versus based on probabilities. So this one is a lazy way when you don't have anything yet, when early on you don't have any simulations that you can draw the switching activities from, then this is a very rudimentary setup. So this report power is really just not very accurate, but will give you some idea. And if you go to page 86, the next page, but you see in here, lower, you see set default switching activity, global activity 20%, and sequential activity 80%, right? So global activity here, meaning that every node is switched 20%. So it is a very, very aggressive switching, and sequential is every flip-flop switch 80%. So this is another very rudimentary setup to give the tool the switching activity. So this is different than the other page where you set the switching activities on the primary input and let the tool calculate the internal switching activities. Over here, you say set all the internal nodes, 4 billion of them, each node switch 20%. So just what it means in here. So when you get a number, that number usually totally bogus, or you use it to over design your or to drive some kind of power optimization. But to be more accurate, you will be providing the VCD or FSDB kind of format. Those are called switching activity files, and they are generated from simulations. And all these leakage dynamic ratio, just to explain further, when you do 0.5, that means that, hey, I don't care, just optimize, dynamic and leakage, same way, meaning give it the same weight. But if you are designing a wireless or handheld application chip, then you want to say leakage is more important. So I give it a 0.7. I think that's what it is. So you can do the man page on this, and you give leakage more weight if you do a handheld application chip. Or if you do a plug-in, very high speed chip, then you do a dynamic, give dynamic more weight. So I just want to add those kind of things.
Thank you, Phil. So just a note aside on the leakage power ops. So in my last project, I work on the 3-nanometer design CPU, right? One of the biggest thing is leakage. So we actually optimize leakage several times throughout the entire flow. So not just post route. So we go through each cycle, and then wherever there is opportunities to downsize from a low VT to HVT cell, we'll do it. So trying to find those where the leakage will be a lot less. So not just one time. So you actually, in real design, you may do it more than once, multiple times. Okay. So area optimization. Why do we want to do it? Okay, so first we want to reduce the design density, right? So once you reduce the density, then remember less density, less congestions, right? So the tool does it. We want to do it when there's no impact to timing, right? Timing is the most important. You have to meet timing regardless of what other ops you do, or whether area or power. So you only operate on a non-timing critical path, meaning timing path that has positive slack. So where you can downsize or remove logic and you still meet timing. So that's where the tool will work on. Okay. So remember we talked about the strategy during placement, right? If you set timing as your strategy, the tool is still, the other two, for example, the congestion is still going to be a target, but it's going to be a second target, like a secondary target. So it will do timing fixes, but then it'll go back and it does error reclaim, meaning that it will downsize, swap out bigger gates for smaller gates, or remove logic where it still need timing. Okay. So basically, just a picture here, you can reduce density. but your die size is fixed, right? I mean, you can't change the die size, this area up, meaning you actually reduce the density, right? Less congestion, not reduce the die size. That's a completely different story. Okay. So not the chip die size, but reduce the density of your design so you have better chance of routing and saving area. Okay, so this is wrong. Okay, so I'm going backwards, sorry. Okay, so we so what happened during area optimization? Like I mentioned before, it works on non-critical timing path, meaning timing path with positive slack, right? So it downsizes, for example, an AX on a timing path where it can downsize AX to 4x and still meet timing. It's going to do that, right? Also, it can, example here, if it can delete inverters and so on, still maintain the logic and also maintain the timing. Okay, so the tool does it automatically as part of the optimization in Innovus, but you can do it explicitly by just do an op area, and is tool is going to go and run the area op and look for opportunities in the positive slack nets. Okay, so this is an Innovus log on the area op. So the keyword is you can search in the log file when you're doing this, you can search for the area reclaim optimization and you see what's happening here. You can see actually the density went down. So after the 6 and 57 pass, density actually went down from 54.33 to 54.31. This design is so small, that's why you see this number barely jump down. But you have bigger design, you should see these numbers go down a little quick, bigger. So you can see we talk the WNS we talked about is works negative slack, and then TNS you can see it still remain the same. So this is a memory, just memory, how much memory that the tool uses of the machine. So Innovus uses as much memory when it does it, and then this is the time it takes. Okay, so and then you can do after the area op, you can do a report area to find out exactly what the area is. So you can do report area. That summary, it give you just a quick table, but if you just do a report underscore area without that summary, it give you a whole bunch of details on each of the instances. So in the lab, I designed called Leon, and then this is instant cal. An instant basically is one cell, right? So this is 34,690 cells, and the total area basically take each of these cells added up, and you get the total area. The inner library unit usually is micron. So this is a way, yeah, you run the op, and then you can find out you can do a report before and after, report area summary before and after. You can see the difference. Assuming that your design have a lot of slack, then you have more opportunities to reduce area. Any question or comments before we move on to the next topic, which is tight cell insertion? So we just went over power and area ops, right?
So if there's no question, I have a comment or question back. So I was going to do the poll, but I ran out of time. So can you students type in the chat? So we have this area optimization, or what we call area reclaim or area recovery. So after you meet timing, right? After you meet all the constraints for timing, you do this kind of area reclamation or area downsizing. It's area reclaim on the top, right? So they call it recovery or reclaim, meaning the, claiming the area back. So this one, but mentioned that, can you repeat why we need to do this? So there are two main reasons, and but mentioned one, but I want you to tell me another reason, right? So so can you tell me, maybe I just say, hey, to reduce congestion. Okay, so given that, is there any other reason why you want to do area reclaim? Yeah, why do we need to do area reclaim in VSI? Yes, that's a question. So, but give you more routing area, that means reduce congestion, that's correct. But I'm looking for another reason. Thank you, Nguyễn Minh Duy. So more routing area, when you do area reclaim, what happens to the area? More space to add buffer or inverter to meet timing of hold. Yes, very good, quick tie. I'm looking for another one. So what happens to the total gate or total logic areas when you do reclaim? Does it increase or decrease? Right. So it will increase, right? You have less areas of active areas. What happens there? What happens to power consumption if you have less active areas?
Yeah.
What happens to the power consumption? Is that higher or lower? So the answer is, you do this cost reduction, no, because the die size already there, right? The die size already fixed. You're not shrinking the size. Lower power consumption.
There
Thank
you
you,
go.
Nguyễn Quang Duy.
That's right.
So it is it both active areas. When active areas are lower, that means leakage power. Leakage power is really proportional to your active areas, meaning gate areas and source drain areas. So leakage power absolutely is going to be lower. That means that you meet timing and you have lower power consumption. That's why you want both timing and power. So your chip will consume less, your battery will last longer, right? But in addition, because of your less active areas, then your switching power will be improved too. Given that sometimes you have smaller gates, you have more short circuit currents, but overall your switching power might improve as well. So thank you. That's it.
Yeah, thank you, Phil. That's my omission on that portion. It should also reduce total power. Okay. Very good, Phil. Thank you. Okay, then topic is tie cell. And so what is a tie cell? Why do we need it? So in the lower geometry, your gates are very thin, right? So when they it can be very easy damage here. Very easy damage, whether through power surge, VSE surge, or could be through the fabrication where they do the etching. So there's antenna built up, and we haven't talked about that. I think Ting will talk about that later in the routing regarding antenna effect. But the tie cell designed to protect the gate inputs of the logic cells. Okay, so we have two type of tie cell. One is called tie high, which is the output is always high. Okay, so you can see here, this is the transistor PMOS and NMOS. So the PMOS drain is going to be connected as an output. So once you connect your input to this tie high, this is going to be always tie high. It's going to pull up to VDD. On the other side, we have a tie low cells, which the NMOS drain is going to tie to the output. So this is the tie low and tie high. So during the placement here, we can insert these cells, and then it will actually replace. So in your netlist, actually, it's going to be next slide. Yeah, I will pause here and I'll go to the next slide in a minute here. Okay, so it's just there's a tie high and tie low cells which you use to protect the input gates. In a larger geometry, like 1 micron back then, we didn't have any tie cell because the transistor are a lot bigger and the gate oxide is a lot thicker, so we didn't have those issues back then. But as you move to low geometry, the gate oxide gets thinner, so we need a tie high and tie cell. Okay, so you don't need to before the tie cell of the input gates people connect it directly to the rail VDD or VSS. There's no issue, but in a low geometry, I want to say it's 130 nanometer and below. That's when I start seeing the tie cells in the technology. Okay, so the tie cells before the netlist before tie cell insertion. So you see the one tick B, one tick B0 in Verilog, and you guys know this is for those who already took Verilog. You know that's the tie low, and one tick B is a tie high. So so in this netlist, the example you can see the netlist before tie cell contain one B0, one B1. So netlist after tie cell insertion. So basically, the tie cell will replace the tie high will replace one tick B1, which is tie high here. Okay, and tie low will replace one tick B0 here. So this is example what happened during the tie cell insertions. Okay, and then the tie cell has constraint. You can specify how many fan out a tie cell can attach to. If you say 10, then you limit the 10 inputs. It can tie only to a max fan of 10 inputs, 10 cells. Okay, and also you can specify the distance, meaning that maximum is, let's say, 5 micron. So you have to connect to cells that's within 5 micron from where its locations. So this, okay, so that's the constraint you can specify. Okay, so in summary, the tie cell inserted and it replaced one tick B, one tick B0 in your netlist, right? So by the time you write out the netlist after tie cell insertion, you should not have any one tick B1 and one tick B0. You should see tie cells get replaced. Okay, and then physically in the floor plan, you should see these tie cells. If you have just a one-on-one, you should see it sit right next to those cells that need to be tied. Okay, so this is the mechanism for adding tie cells. So in Innovus, in the lab, you go through this step. You specify, what's the max fan out and what the max distance is. And also you tell Innovus that this is the 2 tie cell unit, use tie high and tie low. And the command is add tie off. Right. So this is just an example how to select the tie cell. And you can see highlight the tie cells. These are all the tie high and tie low cells within this. Okay. So here's the log file from this command. You can see it added 409 tie cells. Okay, so this number dictated by the by your netlist. Okay, so if you have only a few tie nets, then it's gonna only add a few cells. Right? Okay, so that's really only 2 slides I have regarding tie cell. I don't. So Enfield, do you want to add? Do you have anything to add on the tie cell needs? Why do we need the tie cell?
Yeah, I want to start with a question. Do you students, do you have any questions on these 2 slides? If you don't ask questions, that means that you understand it all, right? Okay, there's a question from Ngô Thái Anh Hào. Why Thai cell can't be damaged like other cells? What make it different than other standard cells? But
you mean as you can see the gates, right? The gates are tied completely. So in the regular cells, the gates actually is not. Let's see, it's actually tied to the drain here, right? Different, and then it's got the path to the ground. So it's got a way to discharge the. It have a discharge path from any of the antenna effect. For example, the plasma, right? So it is actually like a diode. That's like a diode. Diode would go to the ground, so they have a chance to have sketchy charges. Versus here, right? This channel may not be off at all, may not be on at all, right? It depends on the logic state, but here the way it's connected, you can see, right? You have any better answer, Phil?
yeah, I don't know if maybe we can draw. I don't know if that. Maybe see. Can you draw? Let me try to see if I can draw. Okay, maybe I can with my fingers here. So if you look at this, if you have a gate, and if you don't tie high, tie low, then this gate is driven by another gate, previously, right? Maybe another. So this, if it is a 0 or 1, it's driven by this, what Bud meant, right? It's driven by a gate. But if you have tie high, tie low, then this will be directly connected to the VDD. That's when it problems. When you have VDD here and you connect to this gate is not any different than other gates. It's still thin gate oxide because every gate has the same oxide thicknesses. But since you're connecting this gate directly to this VDD, and this VDD connect to a lot of other VDD signals, and it go to the pad, and any spike on the pad or any spike on the grid will present a huge voltage on this gate. So the thin gate oxide will rupture. So that's the difference. I hope that understand your question, answer your question, Ngô Thái Anh Hào. If nothing, we can explain further.
Thank you, Phil.
Okay, so any other question about tie cells? You need to ask question why certain constraints are needed. And if you don't ask questions, I assume that you understand why. For example, can you go back to the constraints like max fan out, right? Max distance. Why are these needed? You wonder, right? You can, to be a good designer, you don't just say, hey, I want to put 10 or 20 here because I saw it happening in another setup. No, that means you are a button pusher. You need to understand what these, why are these constraints needed, and what value should I pick, right? Can someone explain either chat or perhaps better with voice?
Yeah, don't be afraid. No questions are dumb questions. Those, okay? No question is a dumb question. So just feel free to ask. If we don't know the answer, we'll get the answer for you. Okay.
Yeah, and not everyone knows the answer, including us, experienced person. Sometimes we just do it, right? I'm willing to bet if you ask PD engineers out there who you know has been working for 10 years, 5 years, you ask these questions, they probably won't know the answer. We say, oh, I just use these numbers. But a good leader, we want to train you being a leader, you want to be training you to be innovator who can start a company and own the product versus right now the status of Vietnam Semiconductor is that we can do services, but we cannot do product, meaning that we don't own the technology. If you don't own the technology, you end up working for someone else again and again, which is good, but we really have opportunities here to innovate, to design a product, to design a good product to compete with everyone. You understand all these details will make a difference. So that's why we want to teach you of all these thinking. So it looks like nobody think about it, but can you go back to the tie cell schematic with transistor, right? So in here, you see, so instead of connecting the input of this inverter on the right here directly to VDD, you connect to tie cell. So what happens to this gate? Tie cells, the gate, keep in mind the leakage, right? You have the leakage on the gate. So when you have a leakage, meaning current is been flowing from VDD to this gate, slowly, right? And via this tie cell, right? Via that. So this tie cell, this transistor is really a resistor, right? So when you have current flowing through the resistor, right, what do you have? You have an IR drop, right? So imagine you have 10 of these going very far away. So your IR drop will somewhere at the end of this chain, the IR drop might be too big. And instead of having a VDD, your IR drop, that means you get a lower VDD. So when it's low enough, then you don't have enough high voltage here to have a good logic. So so that's why. So you wanna go back to the other one, but so that's why over here, right? Over here you have fan out. Fan out, that means how many, you have a tie cell here, how many of those gate, right, that you want to tie one tie cell to. And then the distance, this distance is related to, if you have this one very long, then the R will become longer. So you want to limit the distance. So that's the reason why. So knowing all these things, you can make an educated decision on, depending on your technology, you can see what these numbers should look like. Okay, all right, that's all I have.
Thank you, Phil. I think it's a good time to take a bio break. For we could have I only have 2 topics left, so we can have a longer break if needed. Dave, can we have like a 10 minutes break? I need to go to the. I need a bio break.
All right, I'll get you set up with a 10-minute clock, and everybody will see you back in 10 minutes.
Thanks, Dave.